I didn't stop sharing, did I? I don't think I did. All right. So again, if you'd like to resubmit any of those homework assignments, please do so. And just so you guys know, we're going to be doing sections 5.2 and 5.3, and then we will cover section 5.4, and then we will test 5.1 and 5.4. Sound good? Cool. I have no idea when that test is going to be. Probably, maybe, I don't know if it's next week. No, because we don't have school next Friday. So yeah, it's going to be. All right. So number 1 here, evaluate the Riemann sum for n equals 5 for the following equation by taking the sample points to be midpoints. All right, so Riemann sum. Remember that Riemann sum is delta x times the y values, right? Delta x times the y values. Just getting out the quiz review here. Okay. So delta x times f of 1, not f of 1. I should rename that. That's f of x1 plus f of x2. Oh, no. Parenthesis goes inside there. F of x2 plus all the way to f of xi. Right? That's the Riemann sum. Where I is the amount of things that you take, right? Where n is the amount of rectangles that you take. And I is going to be calculated, xi is going to be calculated by using delta x, and well, you'll see here. I feel like we did this start of a similar problem yesterday in class. All right, so delta x. Delta x is b minus a over n. So in this case, 5 minus 0 over, what's my n? 5. Oh, how convenient. Delta x is 1. Perfect. That's really nice. That means the width of each rectangle that I'm taking is 1 unit. Okay. So delta x, the Riemann sum, delta x is 1 times f of x1. Now, how do I calculate x1? Think about it logically. If I start at 0, right? If I start at 0 and the width of my first rectangle is 1 unit, I don't want to use left side approximation. I don't want to use right side approximation. I am told that I want to use midpoint approximation. So if my full length of my first rectangle is from 0 to 1, the midpoint of that is 0.5, right? I'm going to do f of 0.5. You know, what's the true mathematical way to think about it? Remember, xi is going to be a plus, that's hard to say here. Because that was just either it was left side or right side. It's going to be, just think about it logically. Start at your first value, think about how much your delta x is, and go with that midpoint. Right? So in this case, it's 0.5. And then I just keep running I just keep pumping up that value. So instead of 0.5, I'm now going to add a delta x to it to say 1.5. Because think about it this way, the second strip, the second rectangle, is going to go from 1 to 2. So the midpoint from 1 to 2 is 1.5. Same thing here. The next one is 2.5. Then comes 3.5. Then comes 4.5. Do I continue on to 5.5? No, because that is outside of my boundary. You should have n equals 5, which means that you should have 5 y values that you are finding, right? 5 y values that you're finding. And now we just got to figure out what those y values are. The nice thing is I'm multiplying by 1. So if I sum this all up, that's my Riemann sum. That's my area. It's my approximation for the area. So 0.5. I'm going to do 0.5 squared minus 3. 0.5 squared minus 3. I'm going to take that. I'm going to add it to 1.5 squared minus 3. I'm going to take that, and I'm going to add it to 2.5 squared minus 3. I'm going to take that, and I'm going to add it to 3.5 squared minus 3. I'm going to take that, I'm going to add it to, almost hit subtract, plus 4.5 squared minus 3. Again, all I'm doing is plugging it into the function. Did you guys get 26.25? You should have. That's what I got on my key. 26.25. Remember, at that point, you would have to multiply back on your delta x, but since my delta x is 1, multiply by 1, 26 and 4. And again, what is that? That is the approximation for the area under the curve from 0 to 5 of x squared minus 3. So thinking about it visually here, if I've got a parabola shifted down 3 units, that's a minus 3. And I'm going from 0 to 1, 2, 3, 4, 5. Okay, so this is all green area plus purple area, right? Green being negative down below. That's my cumulative area, 26 1/4 units from 0 to 5. All right, questions on number 1? Cool. Number 2. Again, cumulative area here. You just got to know what these notations mean, right? From 0 to 2. Okay, so from 0 to 2, looks like I've got this triangle. So geometrically here, that triangle, 1/2 base times height, looks like my base is 2, my height is 4. So 4 times 2 is 8, divided by 2 is 4. So negative 4. Keep it going. Now, again, that's a negative area because it's below the x-axis, right? Keep it going here. So 0 to 4, looks like I got to add on this rectangle here. Still in the negative direction, though. Rectangle of 2 by 4 units, so negative 12. All said and done? Yeah. Cumulative. Keep adding on. 0 to 5, looks like I've got to add on this chunk, that little trapezoid looking thing. But trapezoid is just a triangle and a rectangle. So it looks like I got 3 boxes plus this triangle here, a 2 by 1 triangle. So 1 unit, right, 1 unit. So 3 plus 1 is 4. So I'm going to go back down. Now I'm adding a positive now. So I'll go back to negative 8. Going up. Next, when they're going from 0 to 7, got to add on this chunk now. And I'm going to split it like that. Because I've got a square here, 4 units. And then a triangle, a 2 by 3 triangle. So 6 divided by 2 is 3. 3 plus 4 is 7. So let's add 7 onto here. Negative 1 cumulative area. And then finally, 0 to 10. It's another 2 by 3 triangle. A 2 by 3 triangle giving us another 3 units. So negative 1 to adding 3 is 2. All said and done, from 0 to 10 should be 2. Questions there? Cool, let's keep it rolling then. You notice the relationship between 3 and 4? It's the exact same equation, right? You should have the exact same answers for numbers 3 and 4, right? If you don't have the answers, the exact same answers from 3 and 4, I would be cautious. Okay. Evaluate the integral by interpreting in terms of area. Use the graph provided with your solution. All right, 2x minus 4. That's just a linear function, right? Y-intercept negative 4. Slope of 2. Rise 2, run 1. And I'm going from negative 2 to positive 4. So on the right side, I need to keep it going until I hit the x value of 4. And on the left side, I need to keep it going until I hit the x value of 2. Down 2, left 1. Down 2, left 1. Okay. All right. No. Notice how there's more space below the x-axis than above? What should my cumulative area be? Negative, right? My cumulative area should be negative. All right, so let's take it piece by piece here. Let's evaluate this rectangle. Looks like I've got a 4 by 8 rectangle, right? So the negative area here would be 4 by 8. That's 4, right? 1, 2, 3, 4. 1, 2. Yeah, that's an 8. 4 by 8. So 2 by 8. So that's 16. Negative 16. Yeah. Good. And then the upper portion here, it's a 2 by 4. So 4 units plus 4. So all said and done, looks like I've got negative 12 altogether. Yes?
When graphing those, how far do you want us to graph them?
go with yeah, the boundaries. Yeah. That's where I knew how to stop. Okay, now what should my answer be for number 4? Negative 12, right? But now let's use FTC2. And FTC2 is the f of b minus f of a, where f is the antiderivative, right? So let's run the antiderivative. We got 2x squared over 2 minus 4x. Right, that's the antiderivative. Bump it up, divide by the power. And that's from negative 2 to positive 4. Top minus bottom, right? Okay, we know that that's just going to be an x, though. Or an x squared. X squared minus 4x. So it's going to be a 4 squared minus 4 times 4 minus the whole chunk of negative 2 squared minus 4 times negative 2. Okie dokie, we got 16. Hey, that just is nothing, right? And on the right side, we get, get that 16 out of there. Negative 2 squared minus 4 times negative 2. And that's going to give me a 12, but don't forget about the negative in front. Negative 12. It's not the exact same answer. Questions on either of those two problems? All right, let's keep it rolling. We've got a lot of problems to get to. All right, if 0 to 10 is 8.5, 0 to 7 is 5.1, and 7 to 10, we're looking to find 7 to 10. Here's what we do know, though. I know 0 to 10 is going to be equal to 0 to 7 plus 7 to 10, right? We do know that property. It does chain together like that. Well, the nice thing is I'm told a lot of these things. 0 to 10 is 8.5. 0 to 7 is 5.1, and I'm looking for 7 to 10. Oh, cool. So 7? 7 is equal to 7 to 10. That's not what I have in my key. What the heck did I do wrong?
5.1 instead of 1.5.
Look at that. It's my little mathlexia there. Okay. Whoops. 5.1. So subtract over 8.5. Oh, what did I say? 3.4. 3.4. Yeah. Much better. Now my answer matches. Questions about that? Cool. All right, I had a lot of people asking me, what's FTC1? What is FTC1? What do number 6? Like, what does that tell me? Remember, FTC1 is the property that says that if you take the derivative of an integral, they are inverse processes, so therefore they will cancel themselves out. So it says use FTC1 to find the derivative of the function. This is the full function. Like, that whole thing is the function. And I want to find the derivative of that thing, right? But the derivative of that thing, FTC1 says the derivative of that thing will cancel the integral. So basically what I'm asking you is do this. Do that. What is the derivative? Well, the nice thing is, just like when you take a square and a square root, they will cancel each other out. If you take the integral of a derivative or the derivative of the integral, they will cancel themselves out, meaning the d over dx cancels with the integral and cancels with this notation over here. The only thing here is that this piece goes in as my variable, right? The 6 and the 5 up top have to come along for the ride. We have 6 up in the numerator. The bottom is 5 plus t, or 5 plus, oops, that's a big plus sign, 5 plus 3x squared minus 2. And then the only thing left to do is, since we've taken the derivative of this whole thing, we kind of peel away the layer of the integral. We have to get at this 3x squared minus 2, which requires a chain rule. The derivative of 3x squared minus 2 is 6x. So multiply by 6x right up to the numerator, and we get 36x over 3x squared plus 3. Can I divide that all by 3? I can. Look at that. Divide that all by 3. 12x is equal to over x squared plus 1. Yeah, there we go. Question. All righty, let's take a look at the next one. Evaluate the integral. Okay, question 7. I'm going fast, right? Evaluate the integral. So this is just straight up using FTC2. I don't tell you to use FTC2, but that's what you should use here, right? It's the easiest route to take. All right, so I've got 6x squared, which is going to turn into 6x to the third over 3 minus 8x squared over 2 plus 5x from 2 to 5. That's really what I'm telling you to do here. All right. The 6x cubed over 3 is 2x cubed minus 4x squared plus 5x from 2 to 5. Okay, plug it in. Plug 5 in. 2 times 5 cubed minus 4 times 5 squared plus 5 times 5 minus the whole chunk of 2 times 2 cubed minus 4 times 2 squared plus 5 times 2. Let's see what it is when I plug in 5. 2 times 125 minus 25 squared is or 5 squared is 25 times 4 is 100. Minus 100 plus 25, that should get me a 175. Yep. Minus, on the right side, that gives me a 2 times 8. 2 to the third is 8. So 16 minus 2 squared is 4. So another 16 plus 10. So 10. 75 minus 10 is 165. Nice when it's polynomial like that. It's pretty easy. All right, let's take a look at another one. Evaluate the integral. Again, don't lose sight of the end goal here, right? Think about 3 radical x, the vertical stretch of 3 on our square root of x. So something like this, right? And I want to go from 1 to 3. From 1 to 3, right? So here to here. This is, whatever I get out, is the area underneath that curve. Let's evaluate it, though. So 3 radical x is going to be 3 times x to the 1/2 power, right? Okay, find the antiderivative. So kick it up a notch. 3 times x to the 1/2 plus 1 is 3/2. Divided by 3/2. And we're going to take that from 1 to 3. Let's reduce that a little bit, though. 3 divided by 3/2. 3 divided by 3/2 is like 3 times 2/3. So 2. 2x to the 3/2 from 1 to 3. Right? I'm doing that right. 3 divided by. Oops. Well, get out of there. Get 3 divided by 3/2 is 2, right? Okay. All right, so let's plug in 3. So we got 2 times 3 to the 3/2 minus, then we plug in 1, 2 times 1 to the 3/2. Let's evaluate. 2 times 3 to the 3/2. That's going to be 10.39 minus, oops, that's not the right thing. Get out of there. 2 times 1 to the 3/2. Actually, that's all just 2, right? Yeah, 2. Because 2 times 1. So 8.39. Cool. Let's keep it rolling. 4 questions left. Plenty of time. Ooh, some trig. Love me some trig. Love it. I miss trig. I really do. You know, it's funny. I was Mr. Delap was doing like one of those like directional problems where it was like, okay, so this guy's traveling due west and he spots a beacon at north 72 degrees west, and then travels for 3 hours, and the new bearing for the beacon is north 75 degrees east. What's the distance from where he's at to the beacon? And I was like, oh, that's so cool. So I did it real quick. It's all fun. Love it. I miss this. I wish I could teach this. Maybe one day. Evaluate the integral from 0 to 2 of 2 cosine x minus sine x dx. All right. What is the antiderivative of cosine? Antiderivative of cosine. Again, think of it this way. Right. The derivative of sine is cosine. Right? So the antiderivative of cosine is just sine. So this is 2 sine x. And then, okay, I've got sine, right? Minus sine here. I know minus sine. I'm going to do this. Let's just think about sine now. What is the derivative of cosine? Oh, I didn't take out that then.
All we have to know is that this is brown.
Oh, this is brown.
This is
Brown. Excellent. How do you? No, she's not. I'm sorry. Oh, thanks. Bye. No, Elena. Who else is this? Yeah, that's it, right? All right, where were we? Oh yeah, we were here with sine, right? Yeah, and remember, what is the derivative of cosine? Negative sine, right? And actually, isn't that what we have right here? We have negative sine. So the derivative of cosine is negative sine, so therefore the antiderivative of negative sine is cosine, positive cosine. From 0 to 2. Notice that again, we're not adding any plus c's onto the antiderivatives here, right? You know, that was back from section 4.9. We always had to add a constant. We never have to do that because in the end, those do cancel out. Get out. 2 sine x plus cosine x. Perfect. All right. So now let's plug in 2. 2 sine 2 plus cosine 2 minus 2 sine 0 plus cosine 0. Okay. I get 2 sine 2. Come on. There we go. 2 sine 2 plus cosine 2 gives me 1.40. Yep. Minus 2 sine 0 plus cosine 0. Plus cosine 1. 0.4. Is your calculator in degree?
I could not tell you.
Radians. It's implied for all these problems. It's implied that the answer is, or the calculations are all in radians.
How did they switch the degrees?
All right, let's take a look here.
I refuse to.
Number 10. Ooh, this looks fun. Evaluate the integral from 1 to 5 of x cubed plus 2x to the 6th over x to the 4th dx. You know, it's interesting to point this out. Everybody look up here real quick. Ooh, maybe not that, but if I just did this. What would be wrong with that statement? Like, why could I never ask you this? What's that? Because it wouldn't be continuous. Because where does it go through? It goes through 0, right? Doesn't the interval go through 0? -1 to 5? And why is it not defined? Because of 0. If I plug 0 into the denominator, no good, right? There's a discontinuity in there. That's why I have to say +1 to 5. I could never ask you something that goes through 0, or anywhere undefined in any function, for that matter. All right, but I don't, so let's not any more about that. X to the 3rd, I'm just going to write this as a polynomial. All right, I'm going to reduce this out a little bit to write it as a polynomial, just uncommon the denominator. And this is going to be x to the -1st plus 2x squared. All right, so that's equivalent from 1 to 5 of x to the -1 plus 2x squared dx. Let's find the antiderivative now. Well, what's the antiderivative of x to the -1st? What's the antiderivative of x to the -1st? ln of x. ln of x. Yeah, ln of x. ln of x plus 2x cubed over 3 from 1 to 5. Yeah, that's the weird one. Because your tendency is to say, okay, kick it up 1, x to the 0 divided by 0? No, you can't do that. So that you know that's red flags. It's got to be an ln. All right, so now let's plug and chug. ln of 5 plus 2 times 5 cubed over 3 minus the whole ln 1 plus 2/3. Right? 2 times 1 over 3. Right, let's figure out what ln of 5 plus that whole thing is. ln of 5 plus, 5 to the 3rd is 125, so 250 divided by 3. 84.94. Oh, I have 83. Oh, no, that's 84.94. Yep. 84.94 minus, and we have ln 1 minus 2/3, which is 2/3. Yeah. Oh, yeah, duh, because ln 1 is 0. But that should be a plus. It should be +2/3. Oopsie, +2/3. I was looking at the minus up here. So 84.94 minus 0.67, I'll just say. 84.27. Oh, I said 84.28, but whatever. 84.27. Alrighty. Last two problems, very similar. Sketch the region enclosed by the given curves and calculate its area. So the hard part here is not only figuring out what it looks like, but also how to transfer what it looks like into an integral, and then evaluate that integral on top of it. So a lot of things going on here. So sketching the graph. I know I have y equals 0, right? That's the horizontal axis. I know I have x equals 7. And then I know I have the square root. 1, 1, 4, 2, 9, 3. Right? Let's go 9. Okay, 1, 1. The square root of square root of 4 is 2. Square root of 9 is 3. So I know this is the area stopping there. That's the area that I'm trying to find. Right? Okay, that means that area is equivalent to 0 to 7 of the function square root of x dx. And that is not so bad to find. What's wrong? Oh, now we have to calculate it. Calculate its area. Okay, so that means we have to do x to the 1/2 from 0 to 7 dx. Take the antiderivative, that is x to the 3/2 over 3/2, right? From 0 to 7. Okay, plug in 7. 7 to the 3/2 over 3/2 minus. Now, the nice thing here is when I plug in 0, what's going to happen? It's going to be 0. So really, I just got to calculate that first part. 7 to the, I'll put it as 1.5 because it's easier, divided by 1.5. 12.35. Yep, 12.35. Any questions on that one? The answer key is already posted, and again, I'm doing a video, so I'll post a video as well. But so if you miss anything along the way or just want to go back and rewatch something. All righty, last one here. We sketch the region enclosed by the curves. All right, we got now y equals 0. That's my horizontal axis, right? But then I've got this 25 minus x squared. What is 25 minus x squared? That's parabola, right? X squared, it's parabolic, it's quadratic. But it's 25 minus x squared. I mean, if you wanted to rewrite it as y is equal to negative x squared plus 25. Okay. Oh, is that a happy quadratic or a sad quadratic? It's a sad one. A is a frowny face. A is negative. Okay. And then this tells me it's going to go up 25 units, right? That's a vertical shift up 25 units, and it's a frowny face. All right, so that means, so 5, 10, 15, 20, 25. That's the area that I'm trying to find. Okay, however, I don't know those coordinates, right? But can we find those coordinates? Oh yeah, that's super easy. That's the zeros of that function, right? That's the zeros of that function. 25 minus x squared is equal to 0. So 25 is equal to x squared. So plus or minus 5 is equal to x. So that's negative 5 to positive 5. So now that I know the area that I'm trying to find, now I can visualize it. I can say, well, that's equivalent to the integral from negative 5 to 5 of 25 minus x squared dx. And now we find the antiderivative. 25 turns into 25x minus x cubed over 3 from negative 5 to 5. Yep. All right, and then we plug in top minus bottom. 25 times 5 minus 5 to the third over 3 minus the big chunk of 25 times negative 5 minus negative 5 to the third over 3. Let's run those numbers. 25 times 5, that's 125. Minus 5 to the third, that's another 125, divided by 3 though. So we've got 83 and a third. 83.3. And this is actually interesting. 25 times negative 5 plus, minus negative 5 to the third divided by 3 is another 83.3, just the negative. And those negatives cancel out to be a big plus sign. And it's 100. It is 166.6 repeating. Or 166.67, which is interesting. Look, I mean, this is symmetrical about the y-axis, right? So honestly, couldn't I have just performed the integral from 0 to 5 and then doubled it, right? Isn't that another possibility that I could have done? All right. Any other questions? Okay, I am going to